we'll talk about the quantum Chern-Simons theory. So I will not say much, in fact, about the Chern-Simons, only about the invariance of links and three manifolds, which you can obtain using it. But still, so Chern-Simons action is as follows. So I'll explain the notation. So suppose that you have an oriented three-manifold M and some principal bundle over it. Then given a connection in alpha in this bundle, so think that I have P, some structure group G over M3, and alpha is a connection. Then, so I will sloppily think about the connection as one form, and then I would like to produce some free form from it. So there are two natural ways to do it. I can either take d alpha, so it will give me a 2 form, and then wedge it with alpha. So I get 3 form, and then I can wedge it with itself 3 times. Right? Now it takes values in the Lie algebra, so I will have some commutators here of these matrices, if you will. So it does not vanish this time. So, and then...
you can think about it. You can think of it now with the matrix as one form.
Yes.
G in each M3 multiplied the matrix.
So this wedge does not vanish. And then you apply the trace, and you integrate this 3 form over 3 manifolds. It's for Chern-Simons. So, and then as in all these quantum field theories, what you in fact would like to study is the integral over the space of all connections. So this is path integral of the exponent of, say, I, K, Chern-Simons of alpha, where K is the number, so this is just a number, some constant that's called the level of the theory. It's just some number. So, you introduce such a functional over the space of all connections. And then you ask yourself, how will it behave when this K, this parameter K, tends to infinity? So then this is a fast oscillating integral because of this IK. So it should, when K tends to infinity, by this stationary phase method, concentrate, if you wish, on the critical points of this action. So the critical points of this action are flat connections. So critical points of Chern-Simons alpha are flat connections.
Just say one sentence about the stationary phase idea. I mean, some pattern.
What was the question?
One sentence about 30 seconds.
About the stationary phase method. So just if you have some exponent of I and then some constant times some function on here, and you take k to infinity, then these integrals oscillate wildly. And when
As you vary alpha, right?
as you vary alpha.
Yeah.
So whenever you're far from some critical point of this functional, it kind of, there's almost no contribution. The main part of the contribution of the connection which contribute to this thing will be critical points of this function.
We see as alpha very slowly now.
Yes, that's much slower. So why is it important in this case? Because then you can just take some critical point of this functional and say, well, let's now see, we know that this point itself contributes a lot. So if you wish, I want to expand the answer in powers of 1 over k. And the first term will be given just by flat connections. But then we would like to see the next term. And then you think, well, then some connections rather close to these flat connections should also contribute. And you would like to compute it. Now, but then you are in the situation which was discussed previously when, so if you would think, let's for a moment forget that the quadratic part is in fact degenerate. So, but let's assume for a second that this set of flat connections is just a discrete set. All the critical points are far from one another. Then near such a critical point, my functional will have only what? So it will not have any linear part since I sit in the critical point. So it will be described by some quadratic part and high order terms. So, and then we can look at these Gaussian type integrals, which are integrals of some quadratic form plus higher additional terms. These higher additional terms were described as the potential. So the only problem here is that, in fact, here we are in trouble because there's the gauge group acting. Here it's a gauge invariant function. So such critical points cannot be discrete. You have all orbits of the gauge group.
I would expect the term coming from the critical points to be one of the square root. And then just sort of the general places to be in the
Yes, okay, yes. So, you're right. So what I should do is just think that I have exponent of I, k, and then some quadratic function, say x squared plus whatever, u of x. Then how to get to the situation which I described before, where I had I, k, x, sorry, without any k, x squared plus whatever function. You just change your variables, right? And the change of the variables is precisely x goes to square root of k x. Okay. And then indeed then you should, since you have here some integration, just think that you have an integration over dxn here, and then this k should appear here in some power of square root of n, and then some other. So you're right. Basically, this square root of k is important. But now, so the gauge group acts. But this was also somehow discussed. And in such cases, we have to introduce these ghosts, anti-ghosts, or this Faddeev-Popov procedure. And it turns out, and so here I'm making my famous quantum. I'm back, guys. The space outside is wild in this hyper tunnel where I disappeared. So I already got my Feynman rules. So I just immediately pass now. I will just tell you what the Feynman rules are. And the nice thing about it is the following. So as you see here, all this, the group, or rather, it's Lie algebra afterwards, are quite important here in this formula. But what we can do is we can go from this formulation, Z, we can go to first to write the sum over graphs whatever graphs I obtain by these Feynman rules, and then there will be a term which describes you some weights. So weight of G, which is given by some integration, the space-time integration, over the set of points x and y, as we were supposed to do in Feynman graphs, given by some space integrals. And then there should be some other data obtained from this graph, which will depend on the Lie algebra. So some Lie algebraic stuff. But here I will just write it formally times G, times its diagram as a graph. And only then making a second step. So here is the first step. Would be to compute some space-time integrals. And the second step would be from G to pass to this Lie algebraic data, which is encoded there. So there will be still the same sum over this G. So the same weight of G. And then times some kind of Lie, Lie algebraic weight of G. Something which I get from this diagram using the Lie algebra. Now, it turns out that just this first step is already sufficient to produce some integrals of three manifolds, and I will now explain also how to incorporate links into this. So we just completely forget, if you wish, about Lie algebras, even though here it's very clear that they appear somewhere and are involved. But we will say something like, well, we know that we can do it for any Lie algebra. And this Lie group can be any compact, simple, etc. Lie group. So I can just say, well, there is some way to pass from this diagram to some Lie algebraic data. But I don't care, since I can do it for any Lie group, or Lie algebra rather, then all I should notice as some common properties of these weights for an arbitrary G, okay, for an arbitrary Lie group. So, and there are such things, so I will explain what do I mean by that, but we will just try to produce, meanwhile, some invariants of three manifolds, which will look like that. Some sum over graphs, some infinite sum over graphs, some number times the graph. And I will just look at it in the free abelian group, meanwhile, generated by graphs. It will not work.
My confusion between group and graph here. Is that G?
Oh, yes. Okay. Oh, this is a graph. Okay. Okay, I'll just remove. I will write Lie algebra, Lie group. Okay. I will never use it again. Yes, yes. G's are graphs.
There are times it's like some kind of buffer from groups and theories.
Yes.
The common part describes the buffer for the contradictory. Sort of the core time.
Now, I will be unable, as we will see, to obtain such a thing in the free abelian group generated by all graphs. And the reason will be simple. It's just, as I said, there should be, in fact, not just G, but some Lie algebraic data or weight related to this G. And even though it should work for any Lie algebra, there are still some common things in all of them. So I should put some relations, in fact, on these graphs. So I will, in fact, consider these graphs modulo some relation. So here I will put these brackets, and this will be an equivalence class of G in, I'll write it sloppily, meanwhile, graphs modulo relations. Now we will see what kind of graphs appear here, what kind of relations, and how to compute these weights. So from this moment, so I will formulate now what kind of graphs appear and how to compute the weights. And this will be motivated, if you wish, by these Feynman rules. But at the moment when I formulate it, I can just forget everything completely, say, I'm over, I don't want to know anything about Chern-Simons theory. No path integrals, nothing. I'm given some series of that sort. Here's the definition. I would like to prove that these are invariants of theory. And that really will work. We'll just completely disregard all these long path leading to it, and we'll use it only as a motivation to write the graphs and the weights. Okay, now, the second question is, okay, suppose that we know how to produce in this way invariants of three manifolds. Now, can we incorporate some links in this approach? Well, yes. If I have an addition to this three manifold, if now I have some link L, so I have a link L sitting in this three manifold, and L is, well, union from 1, say, to M of L i's. This is an M component link. M. So suppose that I'm now given such a link. How should I treat it? How should I insert it here? Well, in this integral, well, just as these correlation functions. Now I would like to think about my observables as about the link components. So I would write something like L1, etc.
Like
L
observable.
M. Sorry. Yes. Okay. So I will write now some correlation function, thinking about these L's just as before I would treat these things. Right? So how did we do that? We would squeeze in some term, a product of terms corresponding to each of these. And here, quite natural way to do it is just to consider the trace and some representation of the holonomy of this connection alpha around each component. So I would take L1, compute the holonomy of this connection alpha around L1, take the trace. And then, etc., times the trace of the holonomy of alpha around L. So this is the way to plug, to incorporate this link, in a sense, in this three manifold. And these guys are called Wilson loops. In physical terminology. And you should just think about Wilson loop as about given knot, and then when you're given a connection, you just compute this trace on the holonomy. Now, before I computed only these correlation functions for the coordinate function, in a sense, for the simplest case. Now, in this holonomy, I can still manage to do it. How? This is so-called path-ordered exponent this holonomy. So I can write it by iterated integrals, by chance iterated integrals. So whatever this is, I will just tell you now the answer, how it should look like.
Why did you make that remark?
So, before I had some, so just I returned to what happened last time. So then when I had some fields phi, z1, zm, and I would just write it as some b phi, the exponent of, say, I, some functional s of phi. Okay, and then there were phi of z1, etc., phi of zm. So, and now instead of these phi, think that I have some more complicated functions. So instead of this phi, there will be some function f of these phi. But of course, it suffices to compute only these correlators, and I can write any other correlators of any more complicated functions by using these guys. So this is what will happen.
The z's in this context are what?
Hmm?
The z's in this formula are in the terms context of what?
So these will be some points. Okay, so
Points where
let me, yes, in space-time.
Oh, they're in space-time.
Yeah, but since I used the holonomy along the knot, I should move these points along the knot. So these will be z's will run along each component of my link. So these legs, so remember in this approach we got some legs and these external legs which corresponded to z1, etc., to zm, they were kind of fixed before, right? And now I will let them run over each link component. So that z1 will run along the first component, etc., zm over m component. And then, in fact, it's slightly more complicated because I will have some these exponents. It will give me, in fact, several points also running over some link component. But in general, these legs will overrun over some knot component. Okay, so what the answer is. So which kind of graphs do we consider? So the graphs which appear, they are the following. So these are unitrivalent graphs. Now why trivalent? So univalent vertices, these are these external legs which correspond to taking this type of correlation functions, right? These are these external legs. And now why trivalent? Well, we've seen in this example of phi cube theory that you have some trivalent vertices because, the potential is cubic. So here you can, guess already that this is a cubical part. So this is a quadratic part and this is a cubical part. So that's why trivalent. Now, there will be some additional data on these graphs, what the data should be. So, with cyclic ordering of edges, I'll just write like that in each vertex. So just take each vertex. There are 3 edges approaching, meeting in this vertex. And I would like to have a cyclic order of these 3 edges. I'll just draw it like that one. No. And not much more. So, how can I draw such graphs? So, let's try to draw such a thing. So, Oh yeah. So and now I will say something about the univalent vertices. So these univalent vertices, these are these guys, kind of the legs, right? So as I said, they will now have to run over different knot components. Now, let's think that I have several legs. Whatever. I have some graph like that with several legs. Maybe more. And I know that these, say, 3 legs should run over the same knot component. Well, let me just draw the knot component here, maybe in some other color.
Why the same?
So, some legs will have to run over the same component, some color. As an example of such a thing. So this, I draw L1, L2, something like that. So if I have several legs which should run over some link component, then just because they sit on this link, and I think that each link component is oriented, they're cyclically ordered in a natural way, the way they appear. So this additional data will be the following. That all univalent legs, they are colored by M colors. So ith color just means that they should all end on the ith link component, if you wish. And then all legs of the same color are cyclically ordered. And so
Are you thinking this graph is actually embedded in your design?
for a moment, not yet. I just think about it as an abstract graph, yeah? Meanwhile, but then we will have to embed them, yes. Or rather the vertices.
Misha, excuse me, how do you achieve this connection between the two red circles, the one edge which comes
From here to here? Well,
does it create a vertex or just
here? No, there's no vertex. Just go. Oh, it's something.
So she has common correlation.
It's just some combinatorics of the diagram. You would just like to take some things of whatever, say of this sort, some kind of graphs of that. And so univalent vertices labeled by, maybe not like decorated. By indices from 1 to n. There may be a repeating index. That's probably repeating. Repeating indices, say these univalent vertex colored by 1, this by 1, this by 1, 1, 1, and these will be labeled with 2. Because I want to think about these univalent vertices as ending on L1 and these ending on L2, even though meanwhile it's an abstract graph. And legs decorated by the same color, I should be cyclically ordered.
Leg is usually a solution.
Yeah. Yes, and legs is univalent. So I'm just trying to think about the abstract graphs, but with some additional data which would more or less correspond to what I should see. So I should see trivalent vertices corresponding to some cubic part of my functional, and these univalent vertices which appear because I take all these traces here of holonomies, this part. And if I have several points ending on the same component, they should be cyclically ordered. So this will be the type of graph.
There is no condition that it should be connected.
No. No, so in this example, it's disconnected. If I remove L1, it becomes disconnected. What I want, though, is I want, as before we said, all these vacuum diagrams should not enter these correlation functions in general, right? So if I have some component with no univalent legs, it does not enter into my formula. So I would like here each connected component of this graph to have at least one univalent vertex. So finally, we say each connected component of G should have at least one univalent vertex as some univalent vertices. These legs. Just because otherwise I will have this vacuum. Yeah? So in a sense, so there are no such components which have only trivalent vertices. So this is
The ones you sort of index them like this, I sub one, first one, second one, third one. So but they're in groups of three, right? There's a group of three, so it's the vertex. There's one solution.
even these, yes?
Please associate with that vertex.
No, I have two orders. So first of all, I have in each trivalent vertex, I have ordering of 3 edges. So these 3 edges are cyclically ordered. But in addition to that, I have some ordering on univalent vertices, of these legs. And here it's this cyclic order, which is given by this red component. So I just don't draw it here additionally, but it goes in this order: 1, 2, 3, 4, 5. Okay, so cyclic order is given by this red circle. Okay, and here it's the same. I fix some orientation on this red circle, and then these 4 are cyclically ordered automatically, just by this red circle.
Well, in the case you don't have any,
Yes.
you don't have any leg.
So I would like, meanwhile, so I'm talking meanwhile about this case when I would like to compute some invariants of links. Right? So you view them as some correlation functions, as kind of m-point correlation functions. So, and in this formula, yes. No, you're right. I should normalize it. This is what, yeah. So I should normalize it by subdividing over the integral d alpha in power I k Chern-Simons of alpha, just by this guy without these. Okay, so you're right. I have to normalize it.
That gets rid of the vacuum.
Yes, and it takes care of it.
Otherwise, we have to do it.
So
are the graphs going to have legs in the manifold differentiation?
yes.
No.
Sorry. In the 3 manifold case, no. So the moment, so there are two things. Let me meanwhile just talk about these links, and then I will talk about 3 manifold. 3 manifolds are in some sense simpler indeed, because I just look at this functional without anything plugged in. So I don't have any legs. I don't have these univalent vertices. So I will just have only graphs which are trivalent. And in case of links, I will have these type of graphs. So now I will just say what the relations should be here, since they're quite simple, and then I will explain what are the weights given by this Feynman rule. So the relations between graphs on graphs as follows. So first there are some anti-symmetry relations. So they're called AS, which stands for anti-symmetry. So the first relation, anti-symmetry, tells you that if at some vertex you change the cyclic ordering of these three edges meeting there, then the graph changes the sign.
So we saw this last night.
Yes, yes, yeah. The reason is that if you take these the algebraic weights, they always satisfy this problem. So it's quite easy. And the second is Jacobi relation. And these things, anti-symmetry and the Jacobi, are the things which, kind of on this diagrammatic level, describe you this Lie algebra. So you have brackets, so you should think that in each point like that you have a bracket. A and B enter, and then the bracket goes out, basically. So it's quite natural that I have it.
The graph theory should never learn about the continuum. Know about Lie algebra.
Here it is, this Lie algebra. So, and then there's the Jacobi relation. The Jacobi relation should have three terms, right? So one of them looks like that. So I'll draw it. Another with this. And finally, I'm trying to draw some relation which would be something like taking the bracket of A and B acting on something else is the same as acting by A, B, and then minus B, A. And I just would like to keep this in mind. And I would like, as I said, to think about this trivalent vertex as something where A enters, B enters, and then A, B goes out, and then it acts on something here. And then, well, this is obviously first acting by A and then by B, which is this term, or acting in the opposite order. First by B and then by A. So, put this relation, which on the diagrammatic level describes it.
That equation applies to
So,
Misha, excuse me. Can you see
so
this?
how to
Can you see this? Jacobi derivative
Yes, so what I can also try to do, I can just try these weights times diagrams, and then I will ask when is this thing an invariant of my link, and then I will see that I should have these relations. I will explain why.
This is the expansion. Can you see it with the Feynman?
Oh, there. This would be hard, because here all this is really involved, all this Lie algebraic data. I don't know how to.
singularity, definitely in singularity. Not in the singularity. I've seen physics papers where they're deriving 4T relations, singularity function. Singularity.
So,
Well, I thought it was something like the fact that you look at degree 4 terms in the internet.
Can't see it classically. Singularity function.
So and then I should also, this kind of, if you wish, a bracket of A and B could act on the white part of my graph, or it could be that I had this vertex ending on my red link component. But then I think that on my link component there's some representation of my Lie group, right? And then that's what I computed here. There were these traces and some representations of the holonomial. So in a sense, this bracket still acts, only now it acts on something like representation of this Lie
Maybe the second
algebra. So here you just see the same thing, yes. This now is understood as acting on some representation. So there are these Jacobi identities.
How would you say that abstractly, the third
This?
one?
Or what? Huh?
Abstractly, the third one, could you say it? I mean, it seems that you assume now embedded in the mind.
So what I'm saying is, I just look at some abstract graphs which look like that. I take free abelian group or vector space, whatever you like, generated by such graphs. And in this vector space, or in this free abelian group, I impose these relations. That's all. So I work on purely formal level. My graphs are formal, not they're abstract. They're not.
His question is, I mean,
So
if the rest of the graph looks like that or like
yes,
that,
I see.
and like
I
this
see.
and
I
like
see. I
this,
see.
they're not the
Yes.
same.
So I think that this is some small fragment of my graph, and I compare here graphs which globally look the same. So outside of this little fragment, which is indicated here, they look precisely the same. And this is a local relation, but which relates any three graphs, which differ only in such fragments.
I'm fine with that. With the next one, I mean, it seems that
With
you
this
have
one?
embedded graphs now. I mean,
No. These are still abstract graphs. This is just, remember that I have some kind of these red lines. They are also pretty abstract for the moment. But they just encode you some cyclic order and of things and color of these legs labeled by the same.
So, Misha,
link
this
component.
overcrossing doesn't matter.
Huh?
This overcrossing doesn't matter.
Yes, this thing is non-existent. I just, okay, I can just draw it if you wish. I can draw it like that. I know that in my graphs I don't have 4 valent vertices. So this is not a vertex. It just comes from my inability to draw it by a planar picture.
But it doesn't preserve the number of legs.
No,
It doesn't.
it doesn't. It changes the number of legs. But it preserves something which I would like to call the degree of a graph, which will be half the number of all, meaning uni and tri-valent vertices. Okay. So here I had 1 trivalent vertex and 1 univalent, and here I have 2 univalent, but at least all the total number of vertices is preserved. Yes?
Did you color there an edge that's not a leg?
So here these are 2 legs, right? So
The red thing is the way he's remembering 6 orders.
yeah. So now this the only difference of these 2 terms is in the cyclic order of these legs.
But the line joining them is not colored.
It's red.
No, the line joining them is not there. Non-existent. That's
It's
not
in a sense meanwhile it's non-existent. Okay, it encodes a not, but so far it's non-existent. Okay, so up to now there were some abstract graphs, and I said what kind of relations are here. I should also, so now what are the weights?
These are like what we call the Feynman rules.
Yes. Well, the Feynman rules encode 2 things. So first, what kind of graphs do I consider? And second, how do I compute the weights associated to these graphs? What do I put on each edge? What do I put on each vertex?
These rules are related to the age of the problem. Right? These relations come from these.
This type of things just appears because here I had cubic part in my cubic type potential. So this leads to these trivalent vertices, and these univalent come from the incorporation of the link. These relations, yes, because of, well, yeah. Well, let me just escape your question. If I'll start to answer, then somebody else will start to bug me, because now I am staying here. I just covered. There's a monster in hiding there. I'm just afraid. If I just slightly show the end of it, and that's just you don't realize what kind of a monster is that. I want my So I will tell you the last minute. But now I will already be safe. So, what kind of weights do I have? So, let me just do it very simply for the flat space. So, I think that I have a link L in the 3 space. Then these Feynman rules become really simple. And then I will already write it okay, maybe I'll write them first as some kind of Feynman rules, and then I will immediately tell you how to compute this weight in some simpler terms. So, okay, so now what I should tell you is the following. So, what do I do when I see a trivalent vertex? And what do I do when I see an edge of my curve? So, first of all, this trivalent vertex, it should be already, it's a point in the space-time. It's a point here. It runs somewhere. And I will have to integrate over the position of this point. Okay, so, and in general, it's an M3, so it will be an R3. Now, I also think that I have some ijk, which are just between 1 and 3. ijk between 1 and 3. These are coordinates in my 3 space, if you wish. And then I take, okay, I will write it with some coefficient, but it doesn't matter. The important thing is that I should integrate over the position of this trivalent vertex, and then I write here epsilon ijk, which is just the totally anti-symmetric tensor in these 3 indices, so it's delta, so it is the sign of 1, 2, 3 goes to ijk of this permutation, if it is a permutation, and 0 if there are repeating indices. So this is the standard thing. And now, when I have such a line here, I just put here, again, there's some coefficient, which is I over 2, and which is inessential. The important thing is, what do I put here? So here, remember that it should be some green function. Yes, it should be the inverse of the quadratic form which I had there. So if you will think about what kind of quadratic form I had there, it looked like curl operator with respect. So now it should be the inverse of curl, and this is given by, so if I have here some, so here I have some points, of course, x and y, which are points in my 3 space, and I have this additional indexing by the 3 coordinates in my 3 space, so it's ij. So it will be, again, epsilon I, j, k. I and j appear here, and over k I will sum, and it's x minus y, the kth coordinate here, over x minus y cubed. Okay, so I wrote some Feynman rules, and then when Yes, and of course when I see a point, already mentioned it before, but still. Finally, when I see a point...
Misha,
Yeah.
can you explain how these indices all of a sudden become coordinates?
These three indices,
Yes.
just forget. These are some...
I mean, that just doesn't make sense.
doesn't make much sense. These are some leftovers, tiny leftovers of Lie algebraic data, in fact. It's funny, but, well, just forget it. It's really unimportant. I will write you now the answer in another form, and it will be rather clear. I just want to get somewhere.
Okay,
Sorry.
your definition of weight G now, right?
Yes, sir. Yeah. So just take it as granted. But if you will think there is a strong relation between what I said before I jumped into the hyperspaces from which I reappeared, and what I'm doing, there is a relation. It can be from it, but it will just take time. So, and then when I see some point Z here, and it's running over some, say, it was on the Lith component. So here I will just integrate over Li. All right. Now, so what kind of way? Yes, yes. Now I will just present it in another form, and it will be more clear without any indices. These indices are. Yes, and this is the point again. And so x, y, and z. These are points in the 3 space. So this x is in my 3 space, again in 3 space. So in general, they should be in this 3 manifold. Now it's just flat.
Z is restricted to line on the
In
left.
R3, but it should be in this Li, which is inside of it.
Part of his name.
So that's how I locally compute. So that's what I do for each vertex, each edge, and each leg. And then I take the product of these over all edges, over all vertices. So what's the final answer is? So the weight of G is given by the following. It's just another description.
Why do you have an interval sign in 2 in the form of on the third one? You sure maybe it should be 1?
You mean here and here and not here? I just think, I had to put it somewhere. I should, in my formula, I had to put some data, some tensors on trivalent vertices and on the edges, and then to integrate overall positions of trivalent vertices and univalent vertices. So I just prefer already to put this integral as part of the data on the vertex. Yes, but you may think that I just have this tensor associated to the vertex. These are the rules, and then I have to integrate over all positions in space-time of these vertices. Another way is just to squeeze it already. So what is the total weight of G? How to compute it? So we consider the following thing. So given this graph G, we consider configuration space of G. Configuration space of G is just the set of all embedding of the set of vertices into the 3 space, which satisfy kind of these properties, so that these univalent vertices should be on the correct node component, etc. So this is the embeddings of the set of vertices of G, including univalent. The 3 space such that embedding, it means that all vertices are distinct. None get into the same point. So it will be a null perspective. So such that univalent vertices, so univalent decorated by I, just go into Li, and on this ith component they appear in the correct cyclic order. So this is the first place where I passed from some abstract graphs to, if you wish, embedded graphs. But I'm only interested, meanwhile, in the vertices of these graphs. So the moment I have this configuration space, this configuration space still has some memory of the graph, if you wish. So I remember that some vertices were connected by edges. And I did not yet use it here in the construction of the configuration space. I never used the edges, only the vertices. So how can I use the edges? Well, I can use the edges to define maps from this space somewhere else. So there is also a map from phi g, I will call it, from this configuration space of G into the product of spheres. Now, this number of spheres is the number of edges. And each copy of a sphere, I should be more precise, I should afterwards rotate it by the whole permutations. Because I don't have any ordering of the edges yet, but it will be sloppy. I think that I will think for a moment that my edges are ordered. Okay? And then by each edge, I will construct here a point on its copy of the sphere. Now, how do I do that? How does the edge give me a point in S2? This is the Gauss map. Just the usual Gauss map. So it just means that I took the points x and y, which are the end points. I connected them by straight line, and I scale this. I already think that it's, I'm again slightly sloppy because then for this the edge should be oriented somehow. So I already think that let's pick some orientations, I don't care which. Our construction will not depend on the choice of these orientations. So this goes into x minus y over x minus y. Well, it has to do something with that. Now, what does it have to do with this formula then? Just the following. If I will try to understand this form, which I held there, this, I can interpret it in the following way. I can say that I took the standard volume form on a two-sphere, so let be omega standard volume form on two-sphere. Now we take, on each copy of the sphere, I take this form, number of edges time. So this gives me a what? On each copy of the sphere here I picked a 2 form. Then I can pull it back by this product of the Gauss maps. So I pull it back now by this product of the Gauss maps. It gives me some form on the configuration space. Now, it's rather easy to check that since my graphs were uni and trivalent, it's rather easy to check that the degree of this form is precisely the dimension of the configuration space. So then if I integrate it, I will get a number. Or rather, I would have it if that would be a closed space. Like that, there's still a question of whether it could diverge. But in fact, it converges, and it gives you the number. And this thing is precisely, well, I should subdivide it by the number of automorphisms of G. This is the factor which already appeared before in these final rules. So and this will be the weight of G. So this is the recipe. This is the final form of this weight. You can just compute it and check that it's correct from this formulation, but you can also do it more formally. So here's the recipe. What I do is I write the sum over all such graphs. I take each graph with its weight, and I take these graphs modulo these relations. Yeah. Yes. Okay. This will to which k? This you mean? Or the parameter? I am taking the expansion and when k goes to infinity, and I'm looking at some terms.
Yeah, which terms?
Oh, all right. Okay. I should. All right. It will be something like 1 over square root of k in power the degree of g. I can. All my relations here preserve the degree of g. So I can separately work on each graphs of each degree. So if I have this infinite sum, I could also make it into some small finite sums the moment I fix the degree. So this I will call z of the link, right? Or maybe, no, the better that. Yeah. And then there's a theorem. So this theorem took many years to prove. There were many people involved. It all started, this formula for the first time, well, without this, but more in this type of thing. It was written in Bar-Natan's thesis. And he have proven it for degree 2, for the two-loop contribution. But he was unable to prove even the... So there are two problems. First problem is the convergency of these integrals. Second problem is why should it be invariant under some deformations of the isotopies of your link. And it turns out that, first of all, that they do converge, and this is due to the existence of the Fulton-McPherson compactification of this space of configurations to which this mapping extends naturally. So you can also do it up over some compactification of this space, and it gives you then well-defined integral already. So we know that it converges. And then the problem is that each coefficient separately is not an invariant. But when you mix them, for all graphs in the same equivalence class using these relations, and the sum of these coefficients is invariant. And this is more tricky. So probably I should I stop? Or if I have 2 minutes, I will explain the general. So I stated that, okay, the theorem. Theorem is very simple. So first of all, it's well defined, by which I mean that all these integrals converge here. And is an invariant of L. Up to isotope, yeah. Of the isotopy class. this is really a link invariant.
So,
Moreover, so I will just let me just finish that. Huh?
to get a really correct statement, you need to talk about frame.
Framed. Yeah.
Well, that's okay. That's okay. It's okay.
Pass off frame. Yes.
Well,
You're right. Yes. If I work with unframed, I should do something else here to add something which is called unframed or frame in relation, which means when I have doesn't matter. Okay. Frame. Moreover, there is a universal finite type. So what does this mean, this universal finite type invariant? Our invariant takes values in some space generated by graphs, modulo the relations, right? In some abelian graph. Right? So any other finite type invariant, in particular Vasiliev invariants with some numerical values, may be obtained by some map, some homomorphism from this group to real numbers, wherever your invariant belongs. So in this sense, it's universal. And finite type means that whenever I fix this degree of G, I just look at the part of some fixed degree, degree n, then this will be an invariant of degree n in the sense of finite type. So this is the statement of the theorem, and this theorem, which all started, as I said, from some statement in Barnatan's thesis, and then there were many people. So Bott-Taubes, Weevil-Vero as a conjecture, and some Axel Rotzinger in case of three manifolds, etc. So there is also a similar statement for three manifolds, and it's all similar. So all these things are linked, and there were many people working on that. So the last account probably of that already, with all things cleaned, is in a paper by Poirier. Sylvain Poirier, unfortunately, it's rather badly written. So hard to read, but at least this is already the final compilation of all these things. So, yeah, of course, I plan to explain how is it related to some compactification of these configuration spaces and to gluing them together. I should say that it's a purely homological construction in some sense. Out of these configuration spaces, I glue them together using these relations by some pieces of their boundary into some huge space. I glue them by kind of, it's not a manifold anymore. I have some open book structure near each, of the top strata. But it's something with a well-defined fundamental class. And what I do is, on the product of spheres, this is clearly top degree form, which I pull here. And since my space, so in general, this sum over all graphs, I can make into one grand configuration space, and I integrate over it. So it's just a standard procedure of a computation of a degree of a map. So.
Talk to begin, but why don't we break, say, for 5 minutes?
How about 10?
What, 10? So we'll be at 10:25.
It's philosophy. It really is. It's completely related. It's incredibly wonderful.
So, this procedure looks as follows. So, algebraic topology way of computing the degree of this map by G. Now, yes. And the simplest case is the linking number. Just the Gauss integral formula for the linking. Now, unfortunately, they all have some boundary. So we should glue them together somehow to make it into a cycle in the big space. Now, what kind of boundaries do appear here? The boundaries, so first of all, I should look at the compactification, and this is the Fulton-McPherson compactification. Yes, so the boundaries of codimension 1, the honest boundaries, will correspond to the following thing. I have a graph, this G, and some subgraph of it, or rather these points, the vertices of this subgraph, collapse, all collide into one point. And then, by this Fulton-McPherson construction, I should blow it up. So I have something which looks like a product of two things. First, G factor gamma, if this was subgraph gamma, and then times the configuration space. By this, I just mean the configuration space related to this thing, times the configuration space of the subgraph itself. So this formula is precisely the one, and then sum over all gammas, right? Okay. So this is precisely the same formula as describes this Hopf algebra structure, the co-product in Dirk Kreimer's stuff.